Okay, so today we're going to go through 21 through 28, and we'll finish off the first portion of the multiple choice test. Um, and then we'll get into and so this is non-calculator, so we'll get into the calculator portion then after that. Okay, so 21. So the number of moose in the national park is modeled by the function m that satisfies the logistic differential equations dm dt is equal to 0.6 m times 1 minus m all over 200, where t is in time is in years and m naught or m0 is equal to 50. What is the limit as t goes to infinity of m of t? This is actually a really simple question if you understand the logistics model, because we know that this number right here is the carrying capacity, so it can't go more than that as n goes to infinity, or in this case t goes to infinity, so the answer is just simply 200. Okay, next question. Okay, so what are all the values for p for which this infinite series diverges, or converges, I'm sorry. So when you look at this, we got a couple things going on. We have n to the p, and this really looks closely to a p series. As a matter of fact, if 1 was gone, it would be n over np, which could reduce to 1 over n to the p minus 1 power. And so that's what we're going to do. We're just going to basically compare it to that. So we know that the sum as n goes from 1 to infinity of n all over n to the p minus or plus 1. Um, and I'm pretty sure I want it to converge. So if it's going to converge, I need to come with something that's bigger than it. So how do we make it bigger? We make the top bigger or the bottom smaller. So if I get rid of 1, it's going to make the bottom smaller, which in turn will make the fraction bigger. So this is greater than or equal to the summation as n goes from 1 to infinity of n over n to the p, which is equal to the summation as n goes from 1 to infinity of 1 over n to the p minus 1. So I want this to converge. Well, the only way this converges is if p minus 1 is greater than 1. So p has to be greater than 2. Okay, so up here, E is my answer. Okay, next question. Okay, so we integrate x sine of 6x. The kind of the mistake that people will make here is they'll just try and integrate x and then sine separately, but you can't do that because they're actually being multiplied times each other. So you'd have to deal with the product rule and blah, blah, blah. Um, so the other thing we could do here is integration by parts. Okay, so we come over here and I'm going to make my u equal to x and my dv equal to sine of 6x. So then I have du is equal to dx, and I have v is equal to, so I have to integrate sine. So integrating sine, you get negative cosine, but then you're also going to have to divide through by the derivative of 6x. So this is negative 1/6 cosine of 6x. Okay, so then plug it into the formula, and the formula is given by u v minus the integral of v du. I'm going to have negative 1/6 this thing times x, I'm just placing the x inside, times cosine of 6x minus the integral of v du. So v du, so minus a negative, so it's a plus. I can bring out the 1/6, and I have cosine of 6x dx, which is equal to negative 1/6 x cosine of 6x plus, now I have to integrate cosine of 6x, which is sine of 6x, but by the reverse chain rule, you have to divide through by the derivative of 6x, which is 6. So this is 1, and the 6 times 6 gives you 36 sine of 6x plus c. Okay, so then going through here and kind of comparing and contrasting, let's see, so negative 1/6 cosine of 6x, so it has to be one of these. So it looks like B is going to be my answer. Okay, 24. Which of the following diverge? Okay, So if you look at this closely, this first one looks super intimidating, but it's really not because you just have to realize that pi is a number and sine of 2 is a number. Now I know sine of 2 is less than 1 because sine is less than 1, and pi is bigger than 3, so this is something close to like 1 over 3 if I was to compare or come up with an estimate for it. So this is like 1 over 3 to the power of n. This is geometric. This is geometric with r is equal to sine of 2 all over pi, which is less than 1. So I know that this converges. Okay, so that's not it. Okay, over here, I know that I can rewrite this as the sum as n goes from 1 to infinity of 1 all over n to the 1/3 power. That's just p series. Okay, so this is p series. P is equal to a third, so therefore it diverges. Okay, and then the last one, well, what's the first thing we're supposed to do? Which we didn't do up here, but what's the first thing we're supposed to do? Check for the nth term test for divergence. So if we take the limit here as n goes to infinity of e to the n over e to the n plus 1, we know this 1 doesn't make a bit of difference as you go to infinity with n, so it's really just e to the n over e to the n, which is 1. And so therefore, this is going to diverge. And it diverges because remember, when you do the nth term test for divergence, if it goes to anything but 0, it's going to diverge. This goes to 1, so it diverges. Okay, so the answer is 2 and 3 only. Okay, next page. Okay, so the function is continuous on the closed interval from 2 to 14, so 2 to 14, and has value shown in the table above. So right away, I know that this is going to be a Riemann sum. This is a very classic type of question. When you see it, you're like, boom, I know that this is going to be a Riemann sum because it gives you a table of the values and it gives you the integral. Like it's a dead giveaway. Okay, but anyway. So as shown in the table above, using subintervals from 2 to -5, that should be +5. Sorry about that, you guys. 5 to 10, and 10 to 14, what is the approximation of 2 to 14 of f of x dx found by a right Riemann sum? Okay, so right Riemann sum, when we do this, we're going to have the integral from 2 to 14 of f of x dx, and this is going to be approximately equal to, because this is a Riemann sum, we're just approximating it. And so we're just making a bunch of rectangles. And I know the rectangles are given. We're going to find the area of each one of them, and it's just base times the height, where the base is the difference between there and there, there and there, and there and there. So the base is going to be 3, 5, and 4. And then the height is going to be determined, since it's a right Riemann sum, it's going to be determined by the number on the right. So in this interval, 12 or 28, 28 is on the right, so it's 28. So we're going to take the base, which is 3, times 28, plus 5. Now 5, it's between 28 and 34, but we're using right Riemann sum, so it's 34. And then plus 4 times 34, or 30, but it's a right Riemann sum again, so we're going to use 30 here again. And when we do this, and I know this because I've done this before, the answer is 374. Okay. I messed up here. This should be, let's see, plus 4 times 30. There we go. Okay, so you have 3 times 28 plus 5 times 34 plus 4 times 30 gives you 374, and that is your answer. Okay, next one. Okay, right away, you should be dreading this. Well, you shouldn't be dreading it, but I know you are because nobody likes this. You know that this is going to be partial fractions. So you know you're going to have to split this apart into two different integrals or two different fractions, and you're going to have to integrate each piece. So away we go. So I'm going to have a all over x plus 2 plus b all over x plus 1 is equal to 2x all over x plus 2 times x plus 1. Okay, So combine these fractions. Now I'm actually just going to ignore, once I combine them, I'm going to ignore the denominators. Remember, if you have a fraction equal to a fraction and the bottoms are the same, well then the tops have to be the same, okay? So in other words, well I guess I'll write it out the first time and then I won't do it again. So I have a times x plus 1 plus b times x plus 2 is going to be equal all over x plus 2 times x plus 1, and that should be equal to 2x all over x plus 2 times x plus 1. Now, what I was saying a second ago was that if these two fractions are equal to each other and the denominators are equal to each other, then the only way that's possible is if the numerators are equal to each other. So I'm simply going to ignore the denominators and just go right to the numerators. Okay? So I have a times x plus 1 plus b times x plus 2, and that's going to be equal to 2x. Okay, so now remember what we do is we choose carefully what we want to let x be equal to. So I'm going to let x be equal to negative 1. This is the equation. It should work for all values of x. So when I plug in negative 1, it should work. Well, if you notice, when I plug it in here, this is going to go away. So you're just going to be left with negative 1 plus 2 is just 1. So you're left with b is equal to 2 times x, but x is negative 1. So this is negative 2. And now I know what b is equal to. Okay, and then I'm going to do it again, and I'm going to let x be equal to negative 2. So when x equals to negative 2, this goes away. This is going to be negative 4, and I have a times negative 2 plus 1, which is negative 1. So this is negative a. Negative a is equal to negative 4, so a is equal to 4. I know I do that in my head, and if you can't do that in your head, that's okay. Just go ahead and take a few minutes and do it to the side. Maybe pause me and go to the side. Okay, so now I'm going to go back up to this integral, and I'm going to rewrite it. So let's go right here. It's kind of getting crowded. So I have the integral of 2x all over x plus 2 times x plus 1 dx, which we know now that we can turn it into the integral of 4 all over x plus 2, because we know a was 4 and over x plus 2, not plus, minus, because b is going to be negative 2, so minus 2 all over x plus 1 dx. Okay, and that's just a natural log. Okay, this is x to the first power. It's nothing big, there's nothing on top, so this is just 4 times ln of the absolute value of x plus 2 minus 2 times ln of the absolute value of x plus 1 plus c. And then we go over here and we take a look at our answer. It looks like it matches up with D. Yeah. Okay, two more. Boom, you should know what this one is. Okay, you're taking the derivative of the integral. This is the second fundamental theorem of calculus. You should absolutely know how to do this. It's a super easy one. So remember the second fundamental theorem of calculus, you just take what's on the top, you plug it in for the variable here, then you multiply it by the derivative of this, minus, you plug in 0 for t, and then you multiply by the derivative of 0, which is 0. So essentially I can just ignore the bottom. Okay, so here we go. So take x cubed and put it in for that. So you're going to have ln of t, which is x cubed, but t is being squared, plus 1. And then minus, you have to plug in the 0, but that just goes away, so it's minus 0. So this is just ln. Oh, wait, I forgot. After you plug it in, remember you have to multiply through by the derivative of x cubed, which is 3x squared. So 3x squared times x to the 6 plus 1. So you come over here and the answer is e. Okay, simple one. Okay, and then the last one. What is the coefficient of x squared in the Taylor series for 1 over 1 plus x squared? Okay, about x equal to 0. Just really Maclaurin. Okay, so you know each term in the expansion is given by the equation f of n evaluated at 0 times x to the power of n all over n factorial. Each term along the way is given by that. So I'm looking for x squared. So if I'm looking for x squared, that has to be a 2, that has to be a 2, that has to be a 2. This is really just evaluating the second derivative at 0 times x squared all over n over 2 factorial. Sorry, over 2 factorial. Okay, now I'm looking for the coefficient. Coefficient is just the number. So the x squared doesn't matter. I just need to figure out what this is. I know what 2 factorial is. It's 2. I just need to compute the second derivative of f and evaluate at 0. So let's go up here, and I have f of x is equal to 1 all over 1 plus x squared. So then um, f prime of x is going to be equal to negative 2 over 1 plus x cubed. Okay, I can rewrite this as 1 plus x to the negative second power. So we take the derivative, bring down the negative 2, which is this. You decrease it by a power of 1, so it goes from negative 2 to negative 3, which is why it's on the bottom as 1 plus x cubed. Okay, and then we do the second derivative. So the second derivative evaluated x, do the same thing. This is like the negative third power. So you bring it down, negative 2 times negative 3 gives you 6, all over 1 plus x to the fourth. And now I just need to evaluate this at 0. So it's equal to 6 all over 1, so you get 6. Okay, now notice they're baiting you to go and answer this, but we know it's not that because we have to go back and plug it into this. So 6 all over 2, which is going to give me 3. So the answer is D, which is 3. Okay, and that concludes the first portion of it. Okay, so the next one we'll do is we'll finish up, or we'll start on the graphing calculator portion. Okay, we'll see you later.